but I still feel like 64K coder. So I will try to speak slowly because, as you see, I don't speak English very well. I'm Spanish. I have this strong accent, so I will try to go slowly. This is the title of my presentation. It's quite long, as you can see, rendering worlds with 2 triangles with ray tracing in 4 kilobytes on the GPU. So actually it was quite difficult to choose the title for my presentation because I had this bunch of ideas I wanted to tell you about, and I didn't really find a way to put it all together in a coherent way. So this is a bit a summary of everything I'm going to speak about. I'm going to speak about procedural rendering of images by just using 2 triangles. I'm going to speak about ray tracing and 4 kilobytes. So it's a bit of everything together. I think before, do you know, have you ever seen a 4 kilobytes demo? I guess you have, right? Yeah? Okay, still I want to show a very nice intro that I like.
This angle is horrible. Look at where he is. Look at where he is.
But I can see him and him in the same shot, though.
This is horrible.
But the information is what we're trying to preserve. So I need to get... I'm not so concerned about getting him in the shot as I am getting his shot. Well...
Be a bonehead.
I'll just blow out my sound.
Your sound is going to suck no matter what.
See, I can only zoom so far back.
Right.
I know, that's why I'm saying.
No, I mean I have one of these.
It doesn't really bend that way.
Yes, it does.
I'm going to adjust it a little.
So this is an example of a 4K demo. So for those that don't know about it, the music, animation, real-time rendering engine, textures, if any, everything is inside 4096 bytes. But it's basically nothing. If you just send a mail to your friend saying, hello, how are you? That's already 4 kilobytes almost. So that's the kind of productions that I'm going to speak about. Yeah, a bit also the motivation to speak here is because in the last 2-3 years we had this huge improvement in the performance of the graphics cards, of the GPUs. And this has been very nice for games, very useful for games and so on, for the movie industry also. But for us demo sceners, it was also incredibly nice. And it's not only because we had our demos running faster, it's basically because it allows us to experiment new techniques that we could not do before. And the GPUs in the last 2 years, they have allowed us it was like an explosion of new techniques and new ideas that we could use in our 4K demos. For example, we did many new things, but we also revived many of the old school effects that we were using in the software rendering era, like in DOS and so on. So we have revived voxel engines, ray tracing, and many other things. On top of that, it happens that making intros for the GPU in shaders is very useful also for the size of the productions. So, because basically you write all your demo inside a shader, and this is text-based shaders. They compress very well, and So basically, the GPU is not only allowed for big performance and new techniques, but also it was a new way to compress data a lot and make very tiny production, but still nice looking productions. So as soon as the shaders 3 model came out, all the intro coders jumped into it, because shaders 2 were not flexible enough to do branching, to do many things, but shaders 3.0, it really was something that you could use in a in many ways, so everyone jumped into it very quickly. So still, as an introduction to give you a bit of a context of what I'm going to speak about, the idea is to make an image on the screen, or an animation, a demo, whatever, by just drawing 2 triangles on the screen, or 1 triangle, whatever. You just need to cover the pixels of the screen with something, then you apply a pixel shader to it, and you build an image inside the pixel shader. So you don't use polygons to model geometry, or you don't have sprites to make particle systems. You don't really have geometry, just 2 triangles, and then you have to build your procedural image or procedural scene animations and textures in the shader. Again, just to remind you, everything is inside the 4 kilobytes. So how much is a kilobyte actually? And that's something that we very often forget. Even demo coders that are doing 64K demos or huge demos, even themselves cannot really imagine how difficult or easy it is to make a 4K until they do one. So just to give an idea, you have this page on the left of the screen that represents 4 kilobytes of data. That's actually the source code of the intro we saw in the beginning of the 3D object changing. So that's the code, the byte code of the demo. Then on the right you have this big encyclopedia with many books. That would represent 64 megabytes. That's the size of a big demo today, or of a video, or if you go to NVIDIA site and you download a tech demo, it's around 60 megabytes, 100 megabytes, or in any demo scene production that is a demo, it's also a few megabytes. So that's a bit the difference. So it's really huge what the difference between 4K and a regular production. However, this is probably not a fair comparison, because if you could somehow measure the beautifulness of a demo or a video or something, that would not really be a linear function of the amount of kilobytes you can spend on it. So just because a demo is 16,000 times bigger, it doesn't mean it will be 16,000 times more beautiful, right? So at some point, just because you add more code, it will not look nicer. This is because of many reasons, but for example, there is many problems in computer graphics that we cannot solve yet procedurally by algorithms or by code. So at some point you have to put textures into it so it looks nice. For example, just to give an example, you have the holy grail of terrain modeling today is to be able to make rivers on the mountains or making erosion. So we still don't have algorithms to make erosion and rivers. So if you want to put a river in your demo, you have to put a bitmap there to make the shape of the river. So not because you put more code, it will look nicer. At some point you have to put data also. I find anything exciting on this number, 4K. It's just that I really I really think it's a very interesting competition because one of the nice things of DemoScene is creativity, and you can do many things that you would never do in a regular job as a game programmer or computer graphics programmer in general. There you have some standards that you have to follow. There is some techniques you have to implement, but here in the DemoScene we are really free to try anything we want. And the 4K category is really the place to experiment all these things because you have to experiment, otherwise you cannot put anything nice on the screen. You really have to be creative and have some imagination to bring new techniques. So that's what I like from the 4K category. It would be as interesting if it was 8K or 10 kilobytes. Well, it's 4 kilobytes, but yeah. So, sorry, for those that, well, I guess most of you know how pixel shaders work. If not, basically the pixel shader is something on the graphics card that for each pixel that is drawn on the screen, it allows you to put there some expressions or something so that you can choose the color of that pixel. So basically for each pixel, the graphics card will give you the hand and it will tell you, okay, give me the color you want that I put in this pixel. That means that when you move code from the old school techniques to a pixel shader, you can only do it for these techniques or algorithms that follow this pattern. Like for each pixel of the screen, do something. Do something can be like a plasma, where you choose the color of the pixel based on sinus and cosinus, or it can be a Raytracer or anything that follows this pattern. It doesn't work with other old school techniques like where the algorithm starts with for each object. This is for each pixel, do something, but if it's the other way around, it doesn't work. For example, the old star field, like this Windows screensaver, where you have the stars coming to the camera, that you cannot do it in a pixel shader. Well, you could, but it's not the nice way to do it, the easy way, because that algorithm works like for each star, move it, project it to the screen, and draw it. So it doesn't fit in a pixel shader paradigm. Well, you could still try to do these effects by using multipass techniques, but that could work, but we are not interested on it, basically because it's too much code to do it for a 4K, because we are all the time in the 4K context. And also it's not elegant, and yeah, the simpler something is, the nicer for the 4K demos. So this is one example of an old school effect that you can do today. So basically, most probably most of you have drawn a fractal. If not, the idea is that for each pixel of the screen, you do some complex mathematical operations that they have something to do with chaos theory and with fractal geometry, and finally you have a color that you have to put on that pixel of the screen. So that works very well on the graphics card, and actually this is the perfect example to show the difference between CPU and GPU rendering, because this algorithm doesn't use any texture, therefore there is no bandwidth requirements. So it's pure computations, there is no texture fetches, there is no bandwidth involved here. So it really makes a difference when you run this on the GPU and on the CPU. It's like 20, 30, 40 times faster to do it on the GPU than in a dual core machine. Sorry. This is also another very, very old school effect. It's based on deforming a texture. So it works a bit like this, as you can see here. For every pixel, given the coordinates of the pixel, x and y, you compute some kind of strange formula that you invent. It doesn't really matter what it is. For example, now I'm changing randomly the formula. It's really random. I didn't prepare it, but it always looks nice. So you just evaluate any strange formula. This outputs, again, two values. So you input x and y on the screen, you evaluate a formula, and it outputs two values that you use to fetch into a texture. And then you put the color of the texture on the screen. So this was used long ago because it's very fast, because you can pre-compute this formula. So in the upper part here, you have the software rendering version of the effect as it was done in the 90s. And as you see, it's just fetching from a lookup table and then using this as input for the next texture fetch. So it's really, really fast. And this is another example. You can do crazy things like here. I'm going to speed it up a bit. Yeah. So this is actually a rasterizer inside a pixel shader. So as you know, graphics cards are basically rasterizers. They are good at rendering triangles. Now, pixel shaders are so powerful that you can implement a rasterizer inside the shader of the rasterizer. So it's like a meta 3D engine. I did it yesterday, so it's not very good. Actually, you can see that the textures are moving. They are deforming because I didn't implement correction, the texture coordinates interpolation, perspective correction. But well, still you can transform vertices, project, and rasterize. Actually, the 3D object, the cube in this case, is stored in a texture. So the geometry is in a texture, and then you read it, you transform, project, and rasterize. It's completely useless, but well, this is demo scene, so we do useless things all the time. Yeah, as I was saying, most of the techniques don't really apply to games or anything. We don't care that they are practical. We just have the fun doing it. You can implement metaballs, plasmas, anything you want, all the effects. And it's amazing how fast it is. For those that were programming it in the old days and still remember the frame rates, when moving it to the GPU is like, wow, that's incredibly fast. You can do ray tracing, of course. This is one of the how to say, well, this is one of the things that you most often see in the demo scene, at least before, where we could see many, many ray tracing demos and intros. Well, it's true that in the demo scene we have done a lot of ray tracing, but we have never done real ray tracing. And by real, I mean rendering something else than spheres and planes, but well. Yeah, so this one on the left actually is a 1 kilobyte intro. Just 1 kilobyte, I will show the code. The one on the right is a 4K intro I made, or a demo, that it was actually a test for Pixel Shader 3. And yeah, it was actually my first shader. So if there is any coder here, maybe you have seen this already. This code here, it's OpenGL code, is responsible for making this image on the left, the brown one, Chocolate. So this is all you need to make that effect. This includes opening a window on the desktop, putting the desktop into full screen mode, initializing OpenGL, creating the shader, running it, and so on and so on. So actually, there is 2 columns. The one on the left is the shader, this part here. The rest, everything on the right, is just to set up OpenGL and so on. So this guy is old. He's living in Poland. It was very kind from him. It was very kind because he made the source code open, but it's not very usual in the demo scene. We normally try to hide the code, not because we don't want people to use our secrets, but it's basically because normally code is so ugly that it's embarrassing to show it. But this guy still, he placed the code there, and many people is learning from it, so it's very nice. Actually, I took the code to be able to put his rendering into my slides. You can also do not only ray tracing, but path tracing. For those that don't know it, this is a technique. It's a bit of an evolution of ray tracing, where you use many rays to inspect the 3D setup of your scene, and this allows you to make more complex shading than the usual ray tracer. So here in the ray tracer, here on the left, on the right, sorry, you have some reflections and shadows, but they are very sharp. Like you can actually see the pixels between the shallow and not shallow part. And the reflections are very sharp, like perfect mirrors. While with path tracing, you cast many rays. The technique is called Monte Carlo integration. And this allows basically for soft shadows, fuzzy reflections or diffuse reflections, even global illumination and so on. So these are 2 examples also of path tracing in the demo scene. These are not real time, these are, well, almost real time, but still not real time. These are procedural images. It's a new competition we have in the demo scene, because traditionally we have been doing a lot of real time rendering, but we have discovered that it's also very nice and interesting to do non-real time rendering. These were 2 examples that actually, the one on the left was second position on Breakpoint in Germany this year, and the one on the right, I think it was second position also in Wensley in Switzerland just a few weeks ago. Still, they don't use global illumination, but you can see the soft shadows and all these techniques. Of course, it's a lot slower because here you only have to cast 1, 2, 3 rays per pixel, while here you are casting hundreds of rays per pixel. But still, you see on the demo scene, we always use spheres, ellipsoids, planes, cylinders, parabolas, boxes, very, very simple shapes. And for some reason, demo sceners, we have never been attracted by real ray tracing. So this is the screenshots of my actual job. This is what I do. I do ray tracing in my job of huge models. This is like 100, 200, 300 million polygons, really huge models. But in the demo scene, we never we have never been attracted by this, and it's really a pity. I would like to encourage everyone to go into real ray tracing beyond spheres and planes. So this is a few screenshots showing ambient occlusion. This is actually running on CPU. It's running on 16 cores or 32 cores, I don't remember now. And it's quite fast. Now the question is, this is a bit off topic, but why not to move ray tracing into the GPU? Real ray tracing, I mean, something like this, like polygons, not just spheres. And there is few reasons why ray tracing has not been moved to the GPU yet, even if it's a very hot research topic. The main reason is that to do fast ray tracing, you need opt trees or KD trees or bonding volume hierarchies or some sort of acceleration structure. And accessing this acceleration structure is quite random or incoherent. It doesn't very well fit on the way graphics cards are built. Graphics cards are built so that when you access memory, you do it in squares, like in a 2D texture. And this doesn't fit at all with real ray tracing. So that's perhaps a reason not to have today yet GPU ray tracing. The other reason is that you need a stack to be able to traverse recursively one of these acceleration structures, and you don't have a stack on the shaders. The day we have a stack on the shaders, things will explode, demo scene included. It will be like the new big step for demo sceners. First was pixel shaders 3, the next one will be having a stack on the shaders. A lot of effects will be possible finally. And the other problem is that you don't have much video memory today on the graphics cards. You have 1 gigabyte, 1.5 gigabytes at most, and that's not enough for most of the real 3D models as well. So, yeah, we are not doing real ray tracing, but we are doing something else on the demo scene today in the 4K, and that's what I'm going to speak about on the rest of my presentation, and that's ray marching. Again, for those that don't know it, in few words, ray marching is a variation of ray tracing, meaning it's a way to inspect the 3D scene. It's based on, well, normally on computer graphics, the main problem to solve is that it's like you are in a given point in 3D, you are looking in a given direction, and you want to know what's there in the 3D scene in that direction. So basically that's ray casting, it's casting a 3D ray, a 3D line from your position to the direction of interest and finding what's there, what's the object there, what's the color or the shadow in that part of the scene. And normally you can do that by mathematically solving the problem. If you are working with spheres, planes, polygons, you can really solve some equations that tell you, yes, there is something here in this direction, or there is nothing there. But for those objects that are not simple, that are not made of polygons, and that therefore don't have a mathematical formula, you have to use this technique for those objects. And it's very simple in conception, it's really, really simple to understand and to implement, and it's incredibly powerful because you can render anything you want with it. So in this case, you have this strange shape here. It's not a sphere, it's not a box, it's something complex, probably without mathematical representation. Yet you can take your starting point, the one in red on the left, take the direction you are interested in, and slowly advance in space and test and do the stupid test, like when you are on the car and you ask your parents, are we there already? Did we arrive to the destination? Yes or no? So you do the same thing. You start going slowly until you hit something. So at each sampling point, at each red circle, you ask the 3D object, okay, did I hit you? I am inside you, yes or no? And if not, you continue to the next step until you hit something. So it's really simple. It's just a for loop and a test, and that allows you to render anything you want. Problem is it's very slow. So that's where GPU comes into the game, because GPUs are very fast. So again, what can you ray-march? Anything you want. You can ray-march height fields or terrains or 2.5 dimension objects, as they call it also. You can ray-march volume textures, so 3D textures with 1 and 0 saying solid or not solid object, so object or not object. You can ray-march procedural isosurfaces like metaballs or anything you want, or analytic surfaces. So actually I have one example of each here. The one on the right is Tracy. You probably know it. It's a 1K intro. The coder is sitting there. He will speak about it probably today or next day, so I don't know when. So this is a height map. It's just a texture, grayscale texture, that tells you the height of the mountains at each point in the base plane. So you can ray-march that. The one on the bottom left is a 3D texture. It's a 256 by 256 times 256 texture. The texels or the voxels contain 1 or 0, saying there is an object here or there is not. And then you can ray-march it by just advancing on the ray through the 3D volume, and when you hit a texel, you stop and you put the color of that voxel. You can also ray-march procedural surfaces, like the yellowish one on the center in the bottom part. That's Tracy. It's also a 1K intro, but by the same programmer. And the surface is made by just some strange formula, like a sinus times something divided by something, and that gives you a kind of potential. And you can find where the potential takes a given value, and that makes an isosurface or a surface, and you can ray-march that. Actually, I'm going to show it. Do you care if I show it? Yeah, because I have been speaking a lot, so it's time for demo. And then we continue. That guy.
Yep.
I think I need some help.
You want to talk about it?
Only talk?
No, I mean, what's the problem?
Problem is I should see my desktop on the big screen.
That is your desktop.
No, I don't have Windows XP, it's Vista. That's an XP thing.
It was worth a try.
There should be some sound on this. Well, anyway. So, yeah, this is...
Did you plug in the sound?
Yeah, should be plugged. And, there it is. Yeah, so that was 1 kilobyte, and if you think about it, just one of these icons you have on your desktop, 32 pixels by 32 pixels, is already 4 kilobytes, 3 kilobytes. And this was 1 kilobyte, and it was covering the complete screen with an animation, sound, very nice colors and shapes. So it's really amazing. Yeah, so you can remark piece of surfaces or analytic surfaces, like the 3D fractal I showed in the beginning. Then you have many ways to really do this ray marching process. So you can do it in the stupid way, meaning the way I explained before, just stepping slowly on the direction of the ray until you hit something. But you have a bit more complex or elaborated ways to do it, like finding. Well, you can recast all this problem into a function root finder problem that is something with mathematics, but well, you have many ways to do it, like dissection and Newton-Raphson mechanisms, and then you have another way to do it, and it's called, I don't know how it's called, I call it like this, distant fields, and that's actually the one I used for that 4K demo on the right, Kinder Neusser, and that's what I'm going to speak about now on the second part of the presentation that is a bit more technical. So it's rendering with distance fields. And I'm going to take this image as an example. This is an image I made for Euskal Party. This is a big party in Spain. You are all invited to go there. It's actually really huge thing, like 5,000–6,000 people there. It's more of a LAN party today, but it was a demo scene party as well. I showed it there. I got first place, and it was on the 4K graphics competition. So meaning you have 4 kilobytes to show an image on the screen. And it was based on ray marching. I did it first on the CPU, then I moved it to the GPU, and I will explain a bit the differences and the advantages to move it to the GPU. So as you can see, it's not trivial geometry, it's not like spheres and planes. You have some more organic shapes, at least, like this monster in the middle that is, it's quite organic. It's not very simple to say if it's done with spheres or cylinders or what. It's something a bit more complex. Then you have not photorealistic lighting, but you have some advanced shading techniques like ambient occlusion or soft shadows. So it's not super complex, but you have a bit of nice techniques. So I will explain a bit how it's done. So, of course, I was not inventing anything new myself. I got many inspiration from many places. This is the two main, well, actually, I discovered one of them after I did the graphics, but well, still I put them here as reference because you can have a look to them to learn a bit more. So there is two works that were done before that were using similar techniques. The first one was done in 1989 by a guy called Sam Dean. This guy was a genius. He was inventing also many virtual reality devices and stuff like this. And he first used it for rendering 3D fractals. In fact, the way I was rendering my Kinder Neusser demo with the 3D fractal, then I discovered it's almost, if not exactly the same thing. Then you also have these guys that made this article for GPU Gens 2, and they were using similar techniques for rendering some parallax mapping effects or relief mapping effects, something like that. So you can go to this article and have a look to it because it's very similar. So basically the trick is to do the ray march, but to speed it up by having some extra information. Like normally you just know if you are inside or not the object. That's the way to do regular ray marching. But if you not only know if you are inside or not, but if you also knew the distance to which you are from the object, then you could really speed up the ray marching process. And basically the rendering with distance fields, it's all about knowing the distance to any object on the scene from any point on space. So this is the idea. So you have the objects, your 3D scene in black, you have your camera or your point of interest in blue, and you have a line that represents the direction you are interested in, the direction you want to know if there is anything there or if there is any color or whatever. So what you do is to take the blue point and somehow compute the distance to the closest object on the scene. So the closest object in this case is this pillar, this capsule here, on the bottom part of the image, and the red line represents the distance from the blue point to the black object. There, you know that there is nothing around you closer than that distance. So that means that you could actually walk in any direction you want, that distance before you hit anything. You can safely walk all that distance, and you know you will not hit anything because the closest object is at that distance. So that means that you can advance in any direction, but also in the direction you are looking to, in the direction of the ray. So that means you can jump up to the second blue point, being safe that you didn't hit anything. If this was regular ray marching, you would have needed, I don't know, 120, 50 steps before you reach the blue point. But here you can really go in one single step up to that point. But that's because you have the information of the distance. So next thing to do is to repeat the process. You are at the second blue point. You again query to the scene, okay, what's the closest object to me? And then the closest object is that one. And you have again in a red line the distance to that object. Therefore, you can walk in a sphere around you all that amount of meters or centimeters before you hit anything. And thus you go to the third blue point. And this you can repeat 3, 4, 5, 6 times, whatever you need before you hit the object. So you actually arrive to the destination point in, let's say, 10, 12 steps instead of thousands or hundreds. So, yeah, the advantages of using this technique is that it's really much faster. It's very simple to do, to program. It's almost as simple as the brute force ray marching, provided you have a way to know the distance to the closest object, of course. But let's say you have a magic function that tells you for this point in space XYZ, the distance to the closest object is this amount. If you have such a function, implementing the ray march is really, really, really simple. It's perfect for 4K or 1K demos. Of course, you can use many, many optimizations here. If you do it in the naive way, in the simple way, it's as I just described on the previous slides. But you can do some shortcuts, like you can afford to have some errors on your distance estimations and on your intersection point, basically. So, for example, if you have a tolerance of 5 inches, and you say, okay, I want to find the intersection, but I don't care if it's very exact. I can accept up to 5 inches of error, or yeah. So then, if you allow for this, then you can take bigger steps. Now, the thing is that the farther you are from the original blue point, the farther you are doing your calculations, the smaller things will become on the screen, right? So in 3D, something when it's very far, it's smaller on the screen. So that means that real-world errors, like the 5 inches, will have less impact when you are doing the error far away from the camera than when you are doing it close to the camera. Then, when doing this ray marching, you can take bigger steps, quite bigger steps than you should when you are far from the camera. Basically, because the objects in screen space, they become smaller with a mathematical relation, like it's like 1 divided by distance. That means that you can make your error proportional to the distance you are sampling. So if you are sampling at 5 meters, you can do it, your error can be 2 times bigger if you are sampling something at 2 meters. Because one compensates the other, so the perspective correction compensates with the error you are making. So this is a very nice trick and a very nice optimization you can use. Of course, as any technique, there is also some problems with it. And the main problem is that the technique becomes very slow when you are not hitting objects, but you are passing through when you are passing very close to an object. Because let's imagine you have a pillar, and you are casting a ray that doesn't hit the pillar, but it just goes like at 1 inch from the pillar. So at some point, the ray marching process goes very close to the pillar, so it knows there is something around. It knows that there is a pillar like at 1 inch distance, so it advances 1 inch, but still doesn't hit it because it's going parallel to the column. So this happens again because it goes parallel, so when you advance 1 inch, you are still at 1 inch from the pillar, and so on and so on. And this happens many times until you really escape from the neighborhood of the pillar, and then the ray marching again accelerates a lot. So hopefully you will not have many such pixels on the screen. You will not have many places where this happens. And actually, this graphics, this image here on the right is showing this problem. So you have the scene again, the graphics, and in colors you have the amount of steps I had to take on the ray marching process before I hit any surface. So bluish colors are very fast pixels to compute because you only give 5, 6 steps. Green are a bit more complex pixels, and red are the really, really slow pixels to compute because you have to give up to 64 steps. You have to take up to 64 steps before you hit anything. And so, as expected, you have many green parts, but you can see, well, I don't know if you can see it actually, but here in the edges, on the borders of the objects, it's like you have a very big increase on the amount of steps you have to take. It also happens on the columns. And it's because of this problem of really going closer to an object, but in a parallel way, not really hitting it. So, but again, the amount of pixels you have is like 5% of the screen space pixels, so it's not very bad. Even if they are very slow, they don't really consume that much. So if anyone is going to implement this technique, I added some numbers as a guide, or, well, just to share a bit my experience with this technique. And these numbers tell you, like, for example, I needed 50 million queries to the distance field function before I could render the image. So if it was a 3D volume, you would be accessing this 3D texture 50 million times for this image. In my case, it was not a 3D texture, it was really a math function, but I have to evaluate it 50 million times. And 60% of these evaluations were used for the primary rays, basically to know which surface you are, it's visible for each pixel. Because as you probably know, if you are going to do shading, like ambient occlusion or shadows, you also have to cast new rays, or basically you need to query the 3D scene information. But still, 60% of the queries were done really just for the basic diffuse shaded image. And this is actually quite interesting because most often when you have highly detailed shading or photorealistic shading, it's quite the opposite. You normally can render very quickly the primary rays or the basic image, and then it takes long to compute the global illumination, the indirect lighting, or the shadows, or whatever. But with this technique, it's the opposite, and that's very, very interesting. And I will explain why in the next slides. So basically, for all this to work, you need a distance field, right? So, as I was saying before, you can do it in many ways, with a volume, with a texture, or with analytic, mathematical representation of your volume, whatever. So, this has been done in the past. But in 4K, you cannot afford to fill a 3D texture with data or anything. So, what I did instead is to think, okay, what if I just define my distance field procedurally, directly? And so that's what I did. But I want to make a point here, and that's that I didn't procedurally create the scene and then compute a distance field for it. Instead, I directly created the distance field, and the 3D surface, the 3D geometry, was a consequence of my distance field. So it's not like I made first the geometry and then somehow computed the distance field. It was quite the opposite. And that's very, very interesting. It's something I never did before, and it turned out to be very fun. And, well, as everything in procedural content creation, in the beginning you don't know what you are doing. You just place there formulas or expressions or whatever, and just something appears on the screen. But after a bit of time, you really master the thing, and you know what you have to type to get a given surface. But it's more complex than when you just do procedural modeling. When you are procedurally modeling something, if you want a shape of a circle, you type the equation of the circle. But this is different because this is indirect creation of geometry. You're not modeling the geometry, but the distance to the geometry. So it's like working in another layer, so it's a bit more difficult. But finally, you can manage and do something interesting. Of course, it's not really that difficult because there is many techniques that you can use, like these ones that are listed here, that I will explain now. like you can combine distance fields together. So if you make an object somehow with the distance field and you make another object, you can combine them together into a single function. You can also repeat objects in any direction you want as many times as you want. You can deform or change the shape of the objects, like twisting or bending. You can add surface details very easily, and so on and so on. So I'm going to explain a bit these examples. So the most easy way of working is to combine small shapes. So let's say you somehow find a way to represent the distance to a box, and then you can take many of these distance boxes and combine them together to give a resulting distance field. Of course, the way to combine them is by using the mean function. So if you have an object here and an object here and you are here, the distance to the closest object is the minimum of the two distances. So the closest object is the one that has more influence, of course. So once you have 1, 2, 3, 10 boxes, you can combine them together in a mean function to get your column or your pillar. So again, you can combine many pillars together by doing the minimum of each one. So in this case, it's 4 pillars, and you can pack them together into one function that is called 4 magic columns or something. So next step is to repeat these columns all over the space. That's something I wanted to do. I wanted to make a graphics that didn't have any boundaries. So I needed to repeat this geometry all over the plane or the space. And the way to do it is very easy. So in a regular way of doing computer graphics, like rasterization or ray tracing, what you should do to have many objects on the screen is to repeat many times the object or instantiate the object many times. That means consuming more memory or consuming more rasterization time or bigger AD trees for ray tracing, whatever. The nice thing on this technique is that you don't really need to add anything. You just have to change the input to your function. So the input is XYZ, of course, it's the point on space. Now, if you want your function to be repeated, if you want your function to become periodic, you just have to make your input periodic. So if you use a mod operation, this is a math operation that is kind of making something like that, that goes from 0 to 1, and then again from 0 to 1, and then again from 0 to 1. If you modify your input like this, then your columns will be there, and then again, and then again, and again, as many times as you want, actually infinite amount of times. And I don't have infinite amount of memory or infinite amount of render time, it's just changing the input. So that's very, very useful. Yeah, you can also distort the image, and I'm saying distorting the image and not distorting the objects, because there is no objects here, it's just distances, and I don't distort objects, but the inputs. Actually, if you want to deform an object, what you have to do is to deform in the inverse way the input to the function. You have to do the inverse transformation to your input, and then you will have on the screen the transformed object. So in this case, for example, I have x by c as input, or p, and I can apply a 2D rotation to the input, actually the inverse of a 3D rotation to the input based on the altitude or the height of the point, and that basically deforms the domain of the function, not the result, but the domain, the input. So it just deforms the space and everything that is inside space, and the 3D object is inside the space in the volume. So it's really deforming space, not really the object. So this is a more practical example that I used for making that monster I had in the image. And the basic idea was a combination of instantiation, deformation, and blending of shapes. So in the beginning I had just one cylinder. Actually it was the one on the right, on the floor, that was representing the x-axis of the volume. Now I could instantiate it 6 times by using the min operation again to combine different shapes. based on how far you are from the center of the object. So when you are close to the center, then it's the sphere that has more influence. When you are far away, it's more the tentacles that drive the final distance value. Of course, to have this blending, well, to control a bit the way the blending happens, I used a smooth step function. You probably know it. Just a function that takes this shape. And what basically it allows you to control the range of values of the input. The range of values. Basically, it allows you to say, okay, from this distance to this distance, and not the other one, but this distance, it will be the sphere that has more influence, and from here to here, it will be the tentacles. So you can't really control where the blending happens. And it's important to use a smooth step function and not just a linear function, because some math features of this function, like the smooth step function, is a cubic function with zero derivatives on the sides. And what that basically means that when you blend both shapes, you don't have a discontinuity on the normals of the surface. So it's really smooth up to the second derivative, so that's important. But smooth step, it comes for free on most GPU languages like GLSL and HLSL, so that's not a problem. And the last technique you can use here without going to the troubles of processing geometry and without having to do very complex things is to add details to your surface. Like this was the basic shapes of the pillars, and I wanted to give them the look of an old corrupted pillar, right? So you take the distance to the pillar and you just add some noise, Perlin noise. And that already makes some holes. So there is no Boolean operations going on here. There is no what is this technique you use in Raytracing, GSM? I don't know how it's called. Well, you don't have to do any Boolean operations on mathematical shapes or in polygons. You just add some noise function. So actually, it's a bit more complex. The FBM function, it stands for fractional Brownian motion. It's a fractal sum of Perlin noises. You have probably used it if you have made 3D mountains or any kind of procedural image. So you have one Perlin noise, you add a second Perlin noise with less influence, but twice the frequency, and so on and so on. So this is done with 4 Perlin noises. And then what is interesting is the clamp function there. So the FBM function, it takes value from -1 to 1. And if I would directly apply the FBM to the distance to the pillars, then I would have both holes into the pillar as you.